theorems for parallelepipeds, and we're going to look at Euler's formula and how Euler's formula works. So remember, parallelograms have 4 sides, and 2 of those sides have to be parallel. Then we have what's called a diagonal of a hexahedron. And so remember, a hexahedron is a 3D shape. So the diagonal is going to go from one corner of the hexahedron, and it's actually going to go through the shape. So it's traveling through the center of the hexahedron. It's not going to be traveling on any of the faces, but it's going to connect one vertex to another vertex, but those 2 vertices don't lie on the same face. So it's traveling through the hexahedron. Here's an example. You see segment AD, how it's traveling through the hexahedron. Okay, but it is not, and that's what we call a diagonal. So segment AD would be a diagonal because it's connecting vertex A and vertex D, but vertex A is not on the same face as vertex D is. So if you look at this one, segment AC, this is not a diagonal. It's not a diagonal of the hexahedron because vertex A and vertex C are on the same face. Now, we would say that AC is a diagonal of the parallelogram ABC, and then whatever that point here is. So AC is a diagonal of this face, but it's not a diagonal of the hexahedron. Alright, and then let's review some other words. An edge, okay, so AB would be considered an edge of the cube. So it would be BC, and so would CD. Here are all the edges, okay, so we can count them. There's 4, and there's 8, okay, and then the connections are 9, 10, 11, 12. So there's 12 edges. Then you have AC is a diagonal of the square, okay, the face of the cube. And then you have AD is a diagonal of the cube. So there's the edge. Here's the diagonal of the face. Here's the diagonal of the cube. Okay, so opposite faces of a hexahedron are faces that have no common vertices. And then opposite edges of a hexahedron are 2 edges of opposite faces that are joined by a diagonal of the parallelepiped. So make sure that if you're looking at opposite, that they are not connected, right? Opposite faces have no common vertices, and opposite edges are going to be on opposite faces. Okay, so here is a parallelepiped again. Here is one face. Here's the other face. So we would say those are opposite faces. So we would say ABCD and EFGH are opposite faces. Now these 2 faces, ABCD and CDFG, are not opposite faces because they share this edge right here, DC. So those would not be opposite. And then we have segment BC, which is an edge. And we have segment EF, And those are opposite edges because look, there's a diagonal that connects E and C, they're vertices, and there's a diagonal that connects F and B, so those are, which are the vertices. And so those are opposite edges. Notice how they're on opposite faces. So BC is on face ABCD, and EF is on EFGH. And we know that ABCD and EFGH are opposite faces, which makes BC and EF opposite edges. Now, if we would look at segment BC and segment AD, those would not be opposite edges because they're on the same face. So they're on the same face, so those are not opposite edges. Alright, so one theorem that we have is that opposite edges of a parallelepiped are parallel and congruent. So they're parallel and then they're congruent, which means they have the same measure. Diagonals of a parallelepiped bisect each other. Remember, if they bisect each other, that means that they divide each other into two equal parts, which means that they have the same measurements, or those two parts have the same measurements. Diagonals of a right rectangular prism are congruent. Then we have Euler's formula, which says V minus E plus F is always equal to 2. So V stands for vertices, E stands for edges, and F stands for faces. So if I knew how many edges something has and how many faces something has, then I could figure out how many vertices that polyhedron has. And likewise, if I knew the vertices and the edges, I could figure out the faces. So all you have to do is plug in what you know and then solve the equation to figure out what you don't know. So here's a tetrahedron. So a tetrahedron has 4 vertices and it has 6 edges. So if I wanted to figure out how many faces it has, so we could count them easily, but let's say I forgot what a tetrahedron looks like. Well, I could plug this information. V is 4 and E is 6. Okay, so 4 minus 6 is negative 2. So remember, all those 3's have to add up to positive 2, which means my F would have to be positive 4, and it is. So faces is 4. There's 4 faces on a tetrahedron. Okay, an octahedron. So let's say, the vertices of an octahedron are 6, and the edges are 12. So again, if I wanted to solve, I could, because 6 minus 12 is negative 6. So I have to have enough faces to make this 2. So if I'm at negative 6, then I need 6 more plus 2 more to make positive 2. So that would be 8. So the number of faces would be 8. All right. That is all for polyhedron today.